that if this is a continuous transformation, or then the unitary operator can be expressed in terms of identity plus a generator times the infinitesimal displacement, and the generator we identified for in case of space displacement, that as momentum. Now that is one thing we I as I said, that I will talk about it in a little more detail after the exam, when you have covered this classical mechanics canonical transformation, that I will explain that why it is exactly momentum. But roughly you can know that without a momentum you cannot have a position transformation. One particle cannot move from another. That is your classical intuitive thinking. And you have also know this statement, which is a mathematical version of this classical intuitive thinking, that momentum is generator of translation. And in the similarly, in the context of energy and time, you will see that we'll think time translation also, like moving something in time, evolving, requires energy in that sense. So energy is a generator of time translation, but that will again that has to be established mathematically. That is what you do in classical mechanics. So that being said, so let us start talking about the dynamical point of view. So what do we want? Let's first discuss that, and then we set up the formalism to do that. So first of all, we are already have discussed that what is time exactly, and modulo all this philosophical discussion. So we identify time as motion of some external object or external clock, a state of external clock, which we consider as a time. And in this case, time will be considered as a parameter, not as an operator. Not operator. That is what we discussed. And even though one can continue to argue that what exactly and how one should define time, so we will rather take it operationally. And we'll think of time, as we know, as an operational parameter. And we will ask that if I am given a state at t0 at a particular parameter value t0, and when this external clock moves from t0 to t, then how the state moves without any measurement. Okay, and you can think this is a natural question, because you can ask this question, for example, if I have this Stern-Gerlach device, SZ and all. So when a beam passes through that, then it involves a measurement, and that it requires a Hermitian operator. But let's say between two measurements, so let's say SZ, so the from here to here. So if that what is coming out of this is a plus z, or some plus n, let me call it some plus n for to be more general. This is n cap, this is m cap. If it is n plus n, then where does it go to this point between two measurements? Okay, so that is the sort of question we want to ask. If you want to ask it in the context of double slit, then you can ask that let's say I have a electron starting from one slit and between two slits, like between two screens. So here the electron is passing through. So let's say I identified it to be here, and then what is the probability, like how do I connect these two states, which is between measurements? Okay, so that is the sort of thing we want to understand. That's what we also did before. So we know already that how to do it in classical mechanics. In classical mechanics, the formalism is that I have a state is given by a q and p, and we want to know what is the q0 p0, how what is qt and pt. Okay? And we know that this is given by q dot del h del p and p dot minus del h del q. And we can integrate these two equations to find qt plus del t of qt plus del h del p delta t, and pt plus del t pt plus minus del h del q delta t. Okay? So this is what we learned already. So somebody is coming in the class, but please join via your ISAR email ID. Otherwise, I have to give permission every time. So this is what we learned in classical mechanics, that if I know the position and momentum of a particle, at time t, I can work out the position and momentum at time t plus delta t using this pair of coupled equations. And you must have also learned that this kind of dynamics, so you must have worked out this form and done this Liouville theorem, that this is sorry, let me put it in more language, space space volume conserved. So it means that if my particle and momentum has some occupies some volume, so dynamics will be such that after some time, if I draw it in another time, then it will be it might get deformed. This phase space might get deformed, but the volume will be conserved. So it can get, let's say, this, but the volume will be conserved. So that was the main essence of classical dynamics. And you can in fact write it as a vector form. You can write this thing as a this thing as some q vector t e to the power lt q0. And if you have not learned this yet, I will talk about this maybe after the midsim. Okay, where L is a Liouvillean. Okay. And we will see that in a moment that in quantum mechanics state, we'll also find a similar kind of expression where instead of this, we'll write psi t is e to the power iht and psi 0. That's what I'll show. Okay. So quantum mechanics can be classical mechanics can be also formulated in this form, and that is the inspiration to build up these dynamics in quantum mechanics. One might also, once I show you how to do all these things, it's pretty simple and easy. But you might think that why did somebody build it up like that? I mean, once it is shown to you, it's easy. But when someone was doing it for the first time, why did they think it that way? Most of the ideas came from classical mechanics, but the crucial ingredients were, in this case, it's not a phase space volume preserving, but it's rather the probability preserving, and we'll show that how to handle that. And as I said, that after the midsem, when you make some serious progress in classical mechanics, we will do one class on to basically shape up all these loose threads, which is from classical mechanics and Fourier transformation, etc. But right now, just know this much of classical mechanics, that is enough. So you learned about Liouvillean already, right? Liouville theorem and Liouvillean.
No, sir.
Okay. Liouville theorem you learned, right? If not Liouvillean. Hello? Are you there? Am I audible?
Yes, sir. We haven't studied that also.
Okay. But you studied only the Hamilton dynamics,
Yes.
and you don't know this point yet that it is phase space conserving dynamics. Okay, I assume that is right, because you are not responding. So it is so one thing just to understand that a classical mechanics is not just any pair of first order differential equation. It is a pair of first order differential equation that preserves total energy and phase space volume. So that point, up to that much, just know that much, and we will build up on that later. It's not very important for quantum mechanics, but just good to know that. Okay. So similarly, you will see that quantum dynamics will also have something similar. So classical dynamics is basically a pair of coupled symplectic equation. So symplectic means for the following. So see, the word symplectic means following. You can write P and Q, P dot Q dot S, 1 0 0 minus 1 del. Actually, you can rewrite it like this. Let me explain quickly once the meaning of the word symplectic. So I can write this pair of equation, this particular pair of equation as qt plus del t, pt plus del t as identity plus write it this way. Okay. So this thing you can alternatively write it as identity plus a symplectic matrix which is 0 1 minus 1 0, or you can write it in this way also. Okay. Is it correct? 1 0 del h del q, and yeah, I think there is something wrong, so let me not go over this right now. I have written some sign I have messed up here and there. Anyway, so I will discuss this thing in detail later. But just know that this has a particular matrix form which has is something called a symplectic structure. But let me just write down the statement. I'll prove it to you later. So pair of coupled symplectic equations. Preserving phase space volume and total energy. So that is the essence of classical dynamics. So we will now talk about quantum dynamics, and you will see what is special about it. So in quantum dynamics, as I said, that what do I want is the following, that I want a state to be starting at alpha t naught and going to alpha t naught to t, and we want to find what kind of unitary operator connects these two states. And we want of course it has to be unitary because it must satisfy the following. It has to be a probability, this two has to be both has to be one, and therefore it must be connected by some unitary operator. Okay. And the second thing we want is that it must preserve the relation between states. So that means, so I can also write it as a little more detailed. U that connects between T to T naught, alpha T naught to T. That must satisfy this. Okay. And we also want it very naturally to be an evaluation of probability amplitude. So it has to be an equation that connects probability amplitude. And why is that? Because let's say I have some state psi. So I can also use the notation alpha, but let's use psi. That psi t naught is equal to some c1 alpha t naught plus c2 beta t naught. So that means it is a, these two things form some complete set of states. It is some eigenstate of some operator. So I can express an arbitrary state in terms of this state, just like spin plus 1 by root 2 and 1 plus z and minus z. Now we want this to be, I should be able to do the following also, that psi t naught at t. So if I know how these basis states evolve in time, then I should know how this full thing evolve. So I should be able to just write alpha t naught t plus c2 eta t naught t. Okay. Or alternatively, I can say that this alpha t naught t, sorry, alpha t naught is basically a linear superposition of some other complete set of state operators, and alpha t is also linear superposition of some the same basic state of operators. So the only thing changes here to here, okay, because this changes, so this also changes. So both are basically some vectors in the Hilbert space or some ray in the Hilbert space, right? Alpha t naught and t are both some space. So if I look at the Hilbert space, so this is my alpha t naught and that have evolved to alpha t, and I should be able to express both of them as some superposition of a complete set of states. So the only thing changes, not the basis, is this coefficients. Okay. So therefore, it must. So this need not be true. This may or may not be true. But the only thing that is true, this since both are probabilities, that a prime, a t naught prime, this must be true. Okay, because both are probabilities. So what we want to find, we want to find a rule, find a set of rule that connect these CS, okay, that connect these CS or these alphas, either way, okay. Either we want to find a rule that go from here to here, or that goes from CT not to CT. Either way, that is what is our goal. So everybody clear about this part? Okay, good. So now we want to also remember there is one more thing we want to use and exploit here, is that u t2 t naught must be equal to u t2 t1 and u t1 t naught, provided t2 is greater than t1 greater than t naught, which means if I go from t naught to t2 and there is an intermediate time t1 somewhere, then the guy that takes me from here to here, the operator that takes me from here to here, and the operator that takes me from t1 to t2 to t1, they must, if I apply them consecutively, I must get that. That's a very logical demand, because if I have a time translation operator, it is also applicable for space translation operator, that takes from one point to another and that point to another point, then the whole operator must be a product of these two operators. Because what I want, I take a state, I apply the first one, which is that is taking from t naught to t, and then I apply the second one. This should be equivalent to applying t2 t naught. Okay. So we are going to use this simple reasonable demand. So let's now write down a differential form of this just like before.
Sir,
Yes.
how did we write there like summation over CA prime T naught whole like square would be equal to
Yeah,
summation
because
CA?
both of them are probabilities, right? Both of them are probability amplitude. Their amplitude sum square must be equal to 1. Right? That is all I write. And that is coming from the fact that this is a unitary transformation. Okay? If it is a
Okay, sir.
unitary transformation, then this has to be true. Can you prove it? Hello, who was speaking? Can you speak?
Yes, sir. Arjit.
Yeah, can you prove this? That why this thing? automatically means this.
The unity transformation means we are going from T naught to T only. So there are like that's why both of the probabilities will have to be equal. So that's why we have equated the amplitudes, right?
Yes, but can you prove that? Yes, no, something has to be there, right? You cannot be silent in the middle of a conversation, one-to-one conversation.
Sir, I don't know.
Okay, so can you write, if I write these expressions, these two things in this and use orthogonality, right? If I use this equality, alpha T naught, and you use on each side, I plug in this, that alpha T naught is equal to C prime A prime and C A prime T naught, and alpha T naught T. Can you prove it now?
Yes, so we can plug in the values in that. So like this CA prime T sorry, the ket A prime would be common in both of them. So the summation would have to be equal because like the total is
Yes,
like the
there is one more property you have to use. So do you know what property is that? Yes, no, something should be the answer, right?
no sir, I don't know.
So you have to use that, right?
Yes sir.
Do you know? Can you prove it now?
किधर गया? Yes sir, yes sir. Now it's like both of them have A prime, so it will be equal since it's equal to delta A prime delta A, like delta A prime delta A prime. So it would be equal to one. So this the coefficients like the probability amplitude will have to be equal. So that's why we have equated them. Uh,
Okay. Okay, good. So now we are going to play the same game as last time, that alpha T naught minus alpha T naught and divided by T minus T naught. We are basically going to define the generator just like last time. That if I go from T naught to T, so then it must be U T naught alpha T naught minus alpha T naught. This is exactly same as last time. So this thing I can call it if T minus T naught is dt and dt is a infinitesimal element, then I can call this thing d alpha t dt in the limit dt going to 0, or actually dt is by definition like that, but let me write by t minus t naught going to 0, and then it is u t naught minus identity divided by t minus t naught acting on alpha t, and this has this uncertainty of the factor. So what is identity? Identity is basically u t naught t naught, which means no transformation, right? That is equivalent. You can alternatively also write it like that. So then I define a displacement operator, a time displacement operator, which is the generator, and that is defined with a modulo e to the power I gamma u, which I can set gamma equal to 0 without any loss of generality. Okay, arbitrary, because we know that always there is a room for an arbitrary phase factor because of the transformation that doesn't change any measurables. So that means I can now write just like before, utt naught as 1 plus t delta t. So here delta t is basically t minus t naught. So I can call it delta t. Okay. And now I want to similarly find this thing that u dagger is equal to identity. So that means 1 plus t dagger delta t, 1 plus t is equal to identity. And if I drop the delta t square term, ignore these delta t square terms, that imply t dagger is equal to minus t. So this has to be an anti-Hermitian operator. Anti-Hermitian operator or yeah. So now I want to identify it with a physical operator, which just same thing we did before. So I'll replace the t by a it prime. So now t is sorry, it not dagger, it prime. So now this thing has to be a physical. It can be a physical operator, and now we can again ask the question that what dimension it should have. So dimension of t prime would be dimension of 1 by time, and that I identify it as energy by h bar, which is again coming from Noether theorem and classical mechanics, that Hamiltonian is a generator or energy is a generator of translation, time translation. So now if I plug it back in this expression, so then what I get, so this expression is nothing but d alpha t dt t alpha t, and now we establish t as IH by h bar. So what I get here is basically d alpha t dt IH bar h alpha t. Okay. Actually, I want it to be, yeah, that is the form. So this is the Schrodinger equation, which is nothing but a differential form of time translation. Okay. And we have already seen that you have already seen this equation in defined context. Like defined context means not using this kind of a bracket, but rather using this wave function, and that can be simply written as, if I put x position kate in both sides, so then it will become nothing but t x alpha t dt h, and this thing is nothing but IH bar d psi alpha x t dt h x prime psi alpha x prime t, and hx prime usually is in for a mechanical system. The Hamiltonian is of this form, p square by 2m plus vx, and we have already discussed that this can be p is minus IH by del x, so h kite square del x plus px, and that is the hxx prime is nothing but this operator del xx prime. So this becomes IH bar d psi alpha xt dt minus h square by 2m del x square plus px. Since it's a delta function, so it is nothing but this. Okay. So this is the Schrodinger equation that you have seen earlier in quantum mechanics, in modern, what was that course, World of Quantum Mechanics course. Okay, everybody is clear up to this?
Sir, can you scroll a bit?
Yeah, here or even up?
Sir, a little more. Yeah, yeah.
Yes.
So here in the second step, like that you did u of t comma t naught. Can you
Hmm.
re-explain this part?
This part.
Yes, sir.
Yeah. So this is t, right? So if this is t, so this definition, this thing is nothing but ut t naught is t times delta t plus 1, right? I'm just rewriting this line.
Yes, sir.
So t times delta t plus 1 is ut t naught, right?
Okay, sir.
So that's all. It's the same thing as displacement, if you remember. Right?
Yes, sir. Yes, sir.
Okay. Any further questions?
And sir, when we are plugging in that value of t prime as capital H by h cut,
Hmm.
then uh, how is that I term coming there?
No, this I, right? So T is
Oh,
an
yes, sir. Yes, sir.
anti-Hermitian operator, right? So I am
Yes,
writing T is equal to IT prime, where T prime is Hermitian, just like before, right? Did you follow the displacement operator case? Because it is
yes, sir. Yes,
a,
sir, I got it
yeah.
now.
So T prime has to be Hermitian. So now if it is a Hermitian, I can identify with a physical operator. So that physical operator I'm identifying with as Hamiltonian or energy, which is because I from my experience that from classical mechanics that Hamiltonian is a generator of time translation. Yeah.
Okay, sir.
Okay. Any more questions? Okay. Good. So now let me give a alternative way to get to the same conclusion. So this is what you will find in Sakurai alternative approach. So U t plus dt t is basically, oh, actually, I think I made a, yeah, I made a sign error. So I want it to be minus IHT. And the reason is that this, then otherwise you will get a minus sign here. So I don't want to get that minus sign, because if I do minus IH, I can take this I here on this side, and then that will compensate that minus sign. Okay. It's a choice. There is no harm if you have a differential equation with a minus sign. Now there is one more interesting thing. Okay, I will come back to that interesting thing later, but let me just do the operational part. Then there is some very deep philosophical aspect, and not just philosophical, some technical and philosophical aspect. So one thing, just notice that although we call it a wave equation, the Schrodinger equation as a wave equation, this is not a traditional wave equation. Why? Can somebody tell why it is not a traditional wave equation? You have done this wave and oscillation course, right? So how does a wave equation look like?
Like y equal to a sine omega t minus kx.
No. That is the solution of wave equation. What is the differential equation look like? Nobody knows how a wave equation looks like. That's a really sad state of affair. Then I mean, how do you expect to learn anything if you have forgotten everything from past? You have never seen an equation of wave, a differential equation of wave. You have never solved a wave equation.
Yes, sir, we solved and seen but forgot.
Okay, and how come the whole class forgot? I think one person can forget, but if a whole class forgets, a matter of very serious concern. Okay, okay, this kind of like sucks out the energy from me that to teach you anything. But anyway, since I have to teach, let me go anyways, because I am afraid that that same thing is going to happen with quantum mechanics also. Within two classes, you will forget everything. So a wave equation has the following structure. So del x square psi is equal to what is it should come as 1 by c square del psi del t square, right? This is the form. Is this correct? C is position by time. Dimensionally it is correct. Okay. Now do you remember that this is the wave equation where c is the velocity?
Yes, sir.
Okay. Now notice that important difference. This is a first order in time, but second order in position, a inhomogeneous wave equation. So and this is both are second order in time. So think about it, that why it is still a wave equation and what is the implication of this first order. So we will come back to this point again. So there is a very interesting difference. And actually, I don't know if you have seen this kind of wave equation appear in the context of heat diffusion in classical mechanics. So that then you will see this kind of del H del X square.
Hello, sir.
Yeah.
Sir, isn't it dou square psi by dou x square?
Yeah, dou square. Of course, that has to be dou square. Okay. This also has to be dou. Yeah. So you will find this kind of equation in the context of heat equation, where you will see that this is del psi del H del T. But there has to be another quantity here, so which will balance the dimension, which will fix the dimension. Both sides has to dimensionally be equivalent. So there is a similarity between heat equation and Schrodinger equation, but not the traditional electromagnetic wave or any other wave. So there is a long, far-reaching consequence of this, and there is a reasoning also for this. So Schrodinger definitely didn't derive this Schrodinger equation using this bracket formalism. Right? So he derived it using some idea from classical mechanics called Hamilton-Jacobi. Again, I will talk about it if later if you have interest in it, but let's just proceed with the standard stuff. And you will know that in 19th century there was a development in classical mechanics where people wanted to understand the laws of physics from some deeper point of view. Like, we know that Newton's law exists, we know thermodynamics exists, we know light follows a straight path in geometric optics, but we don't know why. I mean, they are like fundamental rules. So people wanted to know one deeper level reason. So what people came up with is an optimization principle. So they thought all these laws are some sort of optimization. So that's why you have Lagrangian and all that action principle, that minimize action or extremize action, you get classical mechanics. Extremize time of travel between two paths, you get geometrical optics. Extremize time of extremize energy or free energy, you get thermodynamics, and so on. So this idea also led people to think that if there is a physical optics behind geometrical optics, which means there is a wave structure, why not a classical action extremizing trajectory in classical mechanics have some underlying wave structure? Although nobody thought about any physical reason for that. So people tried to formulate that, and that is the Hamilton-Jacobi, which either you have already learned or about to learn in classical mechanics. So Schrodinger's inspiration was that formalism. So he thought, okay, so let's do something which is action. Action is 1 by time dimension. So but in optics you have time extremizing. Here it is action extremizing. So something of 1 by time dimension, if you try to extremize, the differential equation you get will have one less dimension in time in the time derivative. So that is something you have to work out and see. So that was Schrodinger's interpretation, but Schrodinger's way of thinking. But when he derived the equation and formed so by that time it was already clear there is some wave thing is happening somewhere. But nobody knew what wave is that. Although they derived an equation, which is, of course, even nobody felt that you need a wave equation, but it was just for the sake of a mathematical structure. People have worked it out in Hamilton-Jacobi. Similarly, here people from experiment, people realize there has to be a wave, plus the extra factor is this IH bar that you won't get in classical mechanics, of course. But the interpretation came from Max Born. So Max Born understood this as a probability wave and gave the interpretation of this measurement and all that. Okay. So this is the history of the subject. If you want to understand it properly, I think Sakurai has some discussion on it. But you have to learn a bit of Hamilton-Jacobi in classical mechanics, and most importantly, you have to remember the stuff that you have learned in past. So then only you can understand something non-trivial. But let's proceed from here, where we have worked out Schrodinger equation from bracket, and I have shown that this is exactly the same equation which you have seen before, but instead of a bracket, I write it in a particular position basis. Okay. So here is the alternative approach, which is you will find that in Sakurai. So I can write this as IHDT by H bar, and I use this point that I am going to exploit this particular point I have mentioned before, this relation. Okay. So let's use this relation. So this relation tells you ut plus dt t ut t naught must be ut plus dt t naught, right? T naught to t to tt. So that means this thing is 1 minus I h dt by h bar ut t naught is ut plus dt t naught. So that is limit delta t tends to dt tends to 0, u t plus dt t naught minus u tt naught divided by dt is equal to minus I h by h bar u tt naught. So just rearranging the terms. So now I apply, now I just write it in a compact form. So this thing is du tt naught tt h u tt naught, and that is nothing but, so now I can apply on both sides. This is an operator relation. Okay, this is an operator, this is an operator. Now I can act it, this is a relation between operators, and now I can act these states. State at time t equal to 0, and I get, because this is nothing but alpha t h alpha t. Okay. So this is exactly the same form as before, but I worked it out in a different way. So this is the Schrodinger equation bracket. So basically the point is, if you know ut t naught and how it acts on alpha t naught, then you know everything. So this is the next thing we'll work out. That is exactly also the same way, because we also earlier learned that if I know the differential form, I can work out the full form. It will be an exponential. That's what we'll see. Okay. Now, there are three possible scenarios from here. So let me call it case 1. Now, additional complications can arise from that, where h is independent of time. So that is what is our interest in QM1. But there will be a other scenario where h t is time dependent, and there are two possible things, that h at a particular time at another time don't commute, and h at a commute and don't commute. So these two will learn in quantum mechanics too, and they have some special consequences, because it you will see in a moment that in order to get a finite translation, so let's say I'm going from some t naught to t, and I want to differentiate these between in this, I want to do it in these small combinations, right? So I want to go using u from here to here, another u from here to here, another u from here to here, like that. And now each of these u I can write it as 1 by 1 plus h delta t. And then I have to ensure they are sequence, they are calculated in a particular sequence they are in. Because if I change the sequence, then it's a problem in these kind of cases. So we will deal with this complication in quantum mechanics too. And right now we will do the simplest cases, that h is completely independent of time, so there is no such consequence. But as you know, that can always happen. So let's say you have a magnetic field that is AC. So then h is a function of time. And now you want to do a Stern-Gerlach experiment in that. So then what will happen? So that is a very interesting question. And that is like a huge amount of experiments happens that. So recently there was a talk in our institute on terahertz spectroscopy and all that. That is all about these kind of things like time dependent Hamiltonian, but which means some kind of a high frequency AC field. So let's now talk about this case when H is independent of time. How do you get the full form from the differential form? And the answer is, so time translation is limit, actually use the notation delta t, so that means you have no, this is something I already talked about. So I want to use this fact that I can go from a point t0 to t in small elements, and that is so this thing is more clearly written as this. So t minus t naught is this full interval, and that is divided into n pieces. So t minus t naught divided by n. This to the power n alpha t. And this we have seen earlier. This is nothing but so utt naught, the form of utt naught for finite time translation is okay. And that again you can prove it using this way, that you have a ex 1 plus x squared plus this. So I have used the same identity as before. So using this identity, I can write it in this form. So everybody is clear about this form of a finite time translation. So a differential time translation is this.
Hello, sir.
Yeah.
So I think the expansion you have written is e raised to x, no? So I think there is one 2 factorial, 3 factorial in the denominator.
Yeah. So this is 2 factorial is 2, right?
Yeah, and so on.
Yeah,
Sorry.
of course. So 2 factorial 2, that's why I just wrote 2. Okay. So the differential form of a time translation of a state is this, that how do you connect a two states which are nearby differentially close, and if you want to the full form, which is there is a finite translation, not an infinitesimal, then that is the form. Okay, everybody in the same page?
Yes, sir.
Very good. So now what we'll do, we will do 2 more concepts, which is very simple concept, is that we will evaluate the effect of time translation operator on a generic state. So how do I operationally found it? So now comes to the actual application, that if I'm asked to calculate, how will I calculate the operational part? So for that, I need to use the eigenspectrum of some operator, because earlier I told you that I want to write this alpha t as some C a prime, a prime. Okay. And you will see that it is particularly easy if you use the basis of the generator. This is also true in dynamics, in translation, but here we will use the basis of the generator Hamiltonian. So Hamiltonian is this, and its basis, eigenbasis is this. Hamiltonian is the generator of time translation, of course. Okay. So they are energy eigenstates because they have dimension energy. and they are energy eigenkets. This is energy eigenvalues. Why it is easy? Because in this species, this operator is diagonal, and H is also diagonal. So let's see how it is particularly useful. So I want to express e to the power IH t by H bar as J prime J double prime. So J prime. So that means I can write, use the resolution of identity twice. Yeah. That means, and this is nothing but actually I should, yeah, that is fine. So, and this is right. So now why it is particularly easy? So now let's see how simple it becomes. So alpha t not equal to 0, I can express it at but J primes are energy eigenkets, Hamiltonian eigenkets, alpha t naught. So this is my Cj prime t naught in this notation Ca prime. Okay. So this is my Cj prime t naught. So alpha t is nothing but u t naught, alpha t naught equal to 0. So that means alpha t equal to 0, t is given by okay. So what is this? This is nothing but this acting on this will give me a phase factor, or this will be just this. I am just putting this here, and this is a number, I can bring it here. So I am dropping the notation T naught for the time being. So, or let's keep it. It's not a big deal. So then alpha T is Cj prime T naught T prime, because this is nothing but J prime alpha T naught. So now I know the relation. So this whole thing is CJT, Cj prime T. Cj prime T is Cj prime T naught equal to 0 e to the power minus I. So let me remove this. So I told you that we need to find the relation between Ca prime T and Ca prime T naught. So this is the relation that connects these two, and it is trivial to check that it must satisfy, not only it will satisfy this mod square, it will also satisfy the sum of mod square. So the what is the important difference between these two states? That the whole difference comes in this. So if I want to think it like that, so let's say I express my alpha t in terms of a bunch of states. So j. So j is 1 plus 2 plus 3, like that. This is at t equal to t naught. And alpha at t is nothing but with some number. So c1, c2, c3 and all. So this is c1 e to the power minus I u1 t plus c2 e to the power minus I e2 t by h bar 2 plus 1. So what changed? What changed is that in addition to this number, there is an additional phasor at each point. an additional phasor, and that phasor moves in a certain speed that is controlled by this u1t. Okay? So this thing is a, what is this? This thing is a unit circle in complex plane, like, because its amplitude is 1 and their angle is given by u1t by h bar. Now e1 is large, the angle is high. If e1 is small, when e is small, then the angle is small. So with time, the time is uniform. Time is an external parameter. So with time, this thing will move with this. This thing will move like that. So this thing will move, right? And how fast it moves, that is given by that e factor. So a time translation is boils down to the motion of these phasors. So these are physical. These are an intuitive way to think and remember. This is, you don't need it this way of thinking, but this is just for clarity that what is time translation. Okay, everybody got this up to this and the picture. Questions, comments? Is it clear or not?
Yes.
Okay. So then I will do one small, a very interesting special case, and that's where I'll stop. So just 1 minute. So an interesting special case. And the special case is already obvious from what I did, is that if your alpha T naught equal to 0 is an eigenstate of Hamiltonian, is an energy eigenstate. So then what will be alpha T? It will be just because this is nothing but J. Okay. Or in other words, you can think of this to be for any operator which commutes with the Hamiltonian. Then it will have, this will be EJJ, and this will have AJ, AJJ. Okay. So any operator that commutes with the Hamiltonian will have the same eigenstate, right? Of course, some defined eigenvalue. So if your initial state is some eigenstate of this operator which commutes with the Hamiltonian or the Hamiltonian itself, then its time translation is only a phase factor, nothing but a phase factor. So this is the phase, and that will, the angle will change with time, this particular angle with some axis, and that's the only thing. And that means the probability will not change. The probability will never change, in fact. So that means this, if you calculate some in some basis, let's say some psi. So this is equal to so that means the psi alpha t naught square equal to t naught psi alpha t naught. So that with time, the probability of that state of finding in that a system in that state will not change. So this thing is called stationary state, which means the system is always in that state. So eigenstates are stationary state under time transition. Eigenstates of any operator that commutes with Hamiltonian are stationary states under time transition because of the fact that Hamiltonian is a generator of time transition. Okay? So now the basic task of dynamics. So dynamics is basic task is finding an observable that commutes with Hamiltonian. And then expand any state into the eigenstate of that. So that is the whole game of dynamics, and we'll see in after mid-sem that how we will do various calculations based on that. Okay? But and then we'll make some connections with classical mechanics, and that is where I stop. That is this is the syllabus till mid-sem, And if there is a question, now it's a good point to ask. Is it everything clear so far? Okay, good thing is that you have a whole week now, and there will be no more classes. This is the last class. And as you know, Wednesday there will be a quiz, and that quiz is entirely based on discrete quantum mechanics and all that. And so let me stop recording also.